Hi class, how are you? Hope you're doing well. Good to have you here. Now today we're going to talk about data checking and correlation. This lecture is broken up into two parts. In the first part, we're going to talk about checking parametric assumptions. These are assumptions that are being made about data for the analyses that we're going to run in the rest of the course. And then we're going to talk about how to run correlations in RStudio. So first, let's talk about parametric assumptions. So the most common analyses that we use, including correlation, t-test, ANOVA, and regression, and these are all analyses that we're going to cover from this point forward, are parametric. And parametric means that you're making an assumption about the way the data are distributed in the population. And so if you keep on randomly sampling from your population over and over and over again, and if you start charting that data, then the data should start taking on a particular distribution or the shape that you're assuming. And so that's parametric statistics. And as I've mentioned, the analyses that we're going to cover from this point forward are all parametric statistics. Chi-square tests are the only types of tests that we're going to cover in this course that are non-parametric. And parametric statistics have assumptions that need to be met, and those are specific to each type of analysis, but here are some of the common ones that you might see. And so let me cover these. First, the dependent variable should be continuous. And so this is very important. So whenever you have a continuous outcome variable, then you should know that you need to use one of the parametric statistics that we're going to cover from this point forward. And so the DV can be interval or ratio level. Another assumption is that the data are normally distributed in the population. And so I've shown you a normal curve here, very familiar to you, I'm sure. The technical name for this distribution is actually the Gaussian distribution. And so if you ever hear anybody talking about Gaussian distribution, that's very common in statistical circles, then you know that they mean the normal distribution. And you can check for normal distribution by looking at the shape of the distribution of your data. Then you might check the skewness or the kurtosis. The skewness really talks about whether the data are symmetrical. If you have a positive skew, the majority of scores are bunched over to the left. And so I kind of think of skew as kind of like a skirt, it's like, whoo! So if it's positive, then on the positive side is the edge of the skirt. And then the negative skew is the opposite, where the majority of the scores are bunched over to the right. And the edge of the skew, or the skirt, is on the left-hand side, the negative side. And then there's kurtosis, which talks about the pointiness of the distribution. So you see the three examples here. And so there's leptokurtic, mesokurtic, and platykurtic. So you can commit these strange words to memory for the next time you play Quizzo, or just, impress your date, throw them in conversation and sound smart, or just strange. Now in RStudio, you can request the values for skewness and kurtosis, but you first need to install and open the package Moments, and so you will want to do that. And then once you open it up using library, you can use skewness and kurtosis functions to get those values. Now once you get those values though, you have to interpret them. Now what's tricky about this is that there's no one hard and fast rule about how to interpret skewness and kurtosis numbers. And so let me give you one of the rules of thumb, but this is not by any means definitive. In the research world, it's just something that we'll go by because it's one of the conventions, but it is not the end-all be-all. All right? And so if you see a skewness between -2 and 2, and kurtosis between -3 and 3, then you may have a normal redistribution. So if you have values that fall outside of these ranges, you might begin to suspect that your data are not normally distributed. Now, one graphical way to check for normality quickly is to use the QQ plots. And so QQ plots will plot your actual values in dots and then overlay a line that represents the normal distribution, so what your data would look like if it were perfectly normally distributed. And so the farther away you get from this line, and sometimes you may see data that are kind of like in a S shape or snaking around the line, then you begin to suspect that maybe the data are not very normal. And so QQ plots will give you a quick overview to see if your data look fairly normal or not. You can also test for normal distribution using the Shapiro-Wilk test. And you can use the Shapiro test function in order to run this test. And something to keep in mind about the Shapiro-Wilk test is that the null hypothesis says that your data are normally distributed. And so if you have a significant result, that's actually not a good news. That means that your data are not normally distributed. And so in Shapiro-Wilk test, what you want to see are non-significant findings or large p-values. All right, so now that we've covered a few different ways to check for normal distribution, let's hop on over to RStudio and see how that works. See you there. All right, so here we are in RStudio, your trusty friend, and I've set up my working environment now by setting my working directory and then also attaching my data set. And so just FYI, I have done that work. I'm going to probably just delete this code so that you don't have it in your copy of the code. But please do make sure to set your working directory and then import your data, attach data. This is my data though, so you will have to replace this information. Now what we want to do is to start checking for the normal distribution of our variables. And in order to do that though, if you wanted to check the skewness and kurtosis, you will want to use the package moments. And so I need to install Moments. I think RStudio is already telling me, you have to install Moments because you don't have it installed, but it is in your code. So let's take a look at this. So Moments, and then let's install. Okay. And so hopefully it will stop complaining at some point that I have not had Moments installed. I have just installed Moments. And so I have that in my code here. And then, of course, with a package, you want to load it as well using library. And so let's see if I can load that successfully. Okay, looks good. And then you might remember the code skewness and kurtosis. And so I want to check the skewness and kurtosis of my variables. And let's say I'm just going to go with the first one on the list. I want to check the belongingness at pre. And so let me do that for both. And so let's try running that. Skewness, pretty good. 0.4, relatively low. How about kurtosis? Okay, so getting a little bit higher than expected, but still within the bounds of what we had discussed, which is between -3 and 3, and so acceptable. And if you're curious about it, I am very curious about what that looks like. And so let me just do histogram and then just run it just for fun. Okay, a little blocky. I can see that it's not necessarily like a nice little bell curve. In terms of skewness, it looks a little bit skewed to me, but the numbers check out okay. Kurtosis wise, I am not sure if I can evaluate this just by looking at the histogram. It's a little too blocky for me. But anyway, we see the distribution here. That was just out of curiosity. Now let's try another way of looking at normal distribution to try to see the QQ plot. And so for the QQ plot, you might remember that you actually have to run two things. And so you first run QQ norm, and then you run QQ line. And so let's try that. So again, let me just do, for an example, belongs to, and just as a caveat, these are fake data. Your numbers and your figures will look very different. And so, please don't be surprised if you run this on your data and then you realize that it doesn't look the same. But let me run QQ norm. Okay, so this is our data. And then what happens when we overlay the line that represents the normal distribution? So, this is not exactly falling into a straight line. A little bit of a snaky S going on here maybe. And then I've overlaid the line. And so, it's not lining up exactly on that line. So departing a little bit from the normal distribution. But, that's one way to eyeball and to what extent does my variable's distribution approximate a normal curve. I see some departures around here on the edges, especially on the upper side of the distribution. Now, Shapiro-Wilk test is another way to check for normal distribution, and it's actually a test that will allow you to test your hypothesis. Of course, the alternate hypothesis being that you've departed from the normal distribution, so we actually want this to be a non-significant result. We would use a Shapiro dot test and then your variable in here. And so let me just belong, that is not a variable. Belongs then pre. That would have been a fun variable to see though, belong. Shapiro test. Okay, so you see the results, and do we celebrate and say, yay, we've got normal distribution, or do we say, uh-oh, And so if you've said, we actually say, uh-oh, you're right. According to Shapiro-Wilk test, we depart from normality. And so in a real-life research scenario, you may need to start thinking about, do I need to make adjustments to this variable so that I can run my analysis or not? But we have found out that at least with this relatively stringent test, the data may be departing from the normal distribution. And so this was one example of how to check for normal distribution using a few different ways. Let me meet you over at PowerPoint for further discussion of some other assumptions. Now, homogeneity of variance we'll talk more later on in the course, but just an intuition behind it. And so if you're comparing groups, multiple groups on continuous dependent variables, then you're trying to first check to see if groups have equal variance in the population, and that will be done using the Levene's test, which we'll cover later in the class. And similar to when we test for normality, the null hypothesis is actually the representation of good news, where you see population variance being equal across the groups that you're comparing. And so again, you're looking for p-values that are large in order to say that your assumption is met, and that's good news. But we'll cover the Levene's test more in detail later on in the class. Just wanted to give you a sense of what's coming up ahead with this particular assumption. Now, something that's interesting about these tests for assumptions that bears repeating is that the null hypothesis says that the assumption is met. And so that is actually the outcome that we want, is that we want to be able to retain the null hypothesis. And so you're looking for a non-significant result. And that is actually good news, which is very different from your typical inferential statistics where you're looking for a significant effect. And so for these tests for assumptions, we generally want to go with the null hypothesis. And so please keep that in mind. Another assumption is random sampling. So that says that the data were sampled randomly from the population. And the goal is to get a sample that is representative of the population, which is the reason why random sampling is important. And finally, there's an assumption regarding the independence of observations, which means that each observation, oftentimes each participant, for example, is not influenced by any other. And so what you want to do is to recruit a random sample of unrelated separate individuals and minimize any potential confounding effects that might cut across multiple individuals. One important way to do this is to make sure that the probability of being selected into the sample is equal. Now this is kind of complicated. Here are a couple of examples of violations. So for example, this makes sense, which is to sample multiple kids from the same family when you're trying to get data about kids in general. So because those kids are related and share their environment and parenting and so forth, that does not allow for independence of observations. Now sampling without replacement is a little bit more of a tricky concept. So let's imagine that I have a closed class of 50 students to draw a sample from, and I wanted to sample 5 students. Now if I draw the first person out and don't replace that person, then the remaining sample has a higher probability of getting selected. And so it's important to sample with replacement. So if you think about it, if I take one person out of the 50, then the remaining people, if I don't replace that person, would have 1 in 49 students' chance of getting selected. And then if I select one more, then 1 out of 48 and so on. So if you wanted to keep the probability of getting selected the same, then you want to replace the person who just got selected. So I draw one person and then replace that person. So the rest of the sample still has 1 out of 50 students' chance of getting selected, and so on. Alright, so now that you know a lot about checking data, how about you take a break? I think it's a very good time for a break before you move on to part 2, which is correlations. And so go ahead and stretch your legs, grab your caffeinated beverage of choice, do a cartwheel, high-five someone next to you, whatever it takes to get some blood flowing and for you to feel refreshed. And so go ahead and take a break, and then I'll see you in the next part of the lecture, which will cover correlations. Have fun!